Okay, so welcome to Lesson 3 in this series of lessons on the wave experiments for GCSE Physics. So we're looking at the experiment that looks at waves travelling through a solid, and again we're going to be looking at investigating the speed that the waves travel through the solid. In this case, we're going to look at waves on a piece of string. Now, when an oscillation is put onto a string, as it says in the text here, it's fixed at one end, and at the other end, there's an oscillation put in. So let's say it's at this end that the piece of string is being pulled upwards and then pulled downwards repeatedly to create an oscillation. And that sends an oscillation, a wave down the string to the other end. It then reflects back. And what we get formed is these patterns. So in this first case, what we get is there is overall no movement of the wave at either end, and there is a large movement of the string up and down in the center. So we can get either of these patterns, and the pattern changes as we change the frequency of the wave. So we have, in the first pattern, we have just one place where the wave is going up and down at its maximum in the center. In the second pattern, we have these two maximum places of oscillation here and here, and we've got three positions where the string doesn't move at all. So we have the length of the string is given by L, and we can think about the wavelength of the waves for each of these patterns. So one wavelength, if we remember, a wavelength is where we go from a point on the wave to the same point on the next wave, for example, peak to peak or trough to trough. So here we have across the entire length of the string, we go from being at the bottom all the way to the top, back to the center again. So in terms of this wave, what we have is this part of a wave going up the top and back to the middle again. But we're missing this part. So for a full wavelength, it would have to go from the center to the top, back to the center, all the way to the bottom, and back to the center again. So in this case, the wavelengths, the length of the string is showing half a wavelength. So L is equal to half a wavelength, which means that the wavelength is equal to twice whatever the length of the string is. In this next pattern, we see we go from the center to the top, to the center, to the bottom, back to the center again. So in this case, the length of the string is equal to one wavelength. For the third one, we have going from the center to the top, to the center to the bottom, to the center again. So that's one complete wavelength. And then back to the top and to the center again. So that means that the length of the string is equal to 1.5 wavelengths, or 3/2 wavelengths. So the wavelength is equal to 2/3 of the length of the string. That is the wavelength in this case. Then for pattern D, we've got here we're going from the start to the center to the top, center, bottom, center, and then we repeat all of that again. So here the length of the string is 2 times the wavelength. So that's one wavelength, and that's also wavelength. So the wavelength is equal to half of the length. And then for the final one, we have one wavelength there, a wavelength there, and then this pit is half a wavelength. So overall, the length of the string is equal to 2.5 wavelengths, which means that my wavelength is equal to, so the length is equal to 2.5 wavelengths, so I'll write that as 5/2 wavelengths, which means that one wavelength is equal to 2/5 times the length of the string. 2/5 of the length of the string. It's got 1, 2, 3, 4, 5, and there's 2 of those. Okay, and the other thing to remember is these patterns, what we see is these patterns form as I increase the frequency of the oscillation. So this is for a very low frequency oscillation. And then as I increase the frequency of the oscillation, eventually I form these different patterns. Okay, on the next page, you're asked to plan the experiment. You were shown a video which explains the experiment. It's also described in your revision guide. So you can use the wave equation for waves on a string, and it shows the apparatus and how we do the experiment. So let's take a look at how we might think about planning this experiment. So the first thing we need to think about is the hypothesis. So our hypothesis here really comes from the idea that the wave speed is equal to the frequency times the wavelength. That's our hypothesis. So we can say that, number one, wave speed only depends on the frequency and the wavelength. However, we can say something else. Now, this is something that we would have seen looking at the experiment with the slinky. It doesn't matter if we increase the amplitude of our oscillation, for example, that's not going to increase the wave speed. And in fact, what we found was the wave speed seems to be always constant in a particular material. So what we can say is that we think for our prediction, we can say that change in the frequency should not affect the wave speed, which is calculated from the wave equation. Remember, this is our wave equation. Okay, next we have to define our independent, dependent, and control variables. Now, one of the nice things about physics is it's actually really quite straightforward to do this part, looking at the independent, dependent, and control variables. We're looking to measure the speed of the waves. So what we can change is we can change the frequency. So independent, that is the thing that we're changing. So we're going to change the frequency on the wave of the oscillation until we get one of the wave patterns forming. Then what we will measure is the wavelength. And that will be used to calculate wave speed. So it's really wave speed that we're interested in from the title of the experiment, but we're going to calculate that by measuring the wavelength for different values of the frequency and then using our wave equation to calculate the wave speed. And control variables, well, here are some of the things we keep the same. We're going to keep the length of the string the same, and we're going to keep the tension on the string the same. So that means that we're going to use a mass to hold the string taut, and we're not going to change that once we've set it up. Okay, equipment. Identify equipment and describe the method. So the method, remember, is a step-by-step guide. That's described inside your revision guide, so don't propose to write that out here. You can check in your revision guide or on the video to see what the method is. But I will put in a little diagram for the equipment so that we're clear about what each piece of the equipment does. So here we have the diagram for the equipment. We've got something called a signal generator. SIGGEN for short, and that's connected to a transducer. Now, a transducer is something that changes typically electrical signals into some other form of energy. In this case, it's transforming electrical signals into the movement of the oscillating plate on the vibration generator. So we call this a vibration transducer, and all of this together, we can call this a vibration generator. Now the piece of string is attached to the top of this, so that's what's going to cause the string to move up and down, because this plate moves up and down, and we can control how quickly this moves up and down, or in other words the frequency that this moves up and down with the signal generator, so we can control the frequency of the oscillations on the string. Okay, this is sitting on some sort of table. At the end of the table we have a pulley system. So we've got the string goes across the pulley, and on the other end we have a mass. So the pulley is fixed on the table, and this is our piece of string, and this is of a certain length. As usual, when you are talking about the method for an experiment, it's important that you describe what you're going to measure, but also how you're going to measure it. So for example, for measuring the length of the string, you would have the string which is at a fixed length that remains fixed, that doesn't change during the experiment, but you measure this with a meter rule or meter ruler. The frequency is controlled by the signal generator, so you read off this frequency from the dial on the signal generator. So it's important when you're describing how you're making these measurements that you talk about the equipment that you use to make the measurements. So the frequency is coming from the setting on the signal generator by reading the dials. The length of the string is measured using a meter rule. And in terms of control variables, we say that the mass, which is what creates the tension on the string because it's pulling the string downwards, this remains the same, isn't changed, and the distance between the transducer and the pulley doesn't change, so the length remains the same. Okay, so you need to include a step-by-step guide for the method. You could use either a list of steps, or what's sometimes quite a nice way to show this is use a flow map where you show each of the individual steps needed for the method. And the nice thing about the flow map is you can have, as you do the flow map and you have a step, let's say this is measure length of string. So this is my flow map. What you can add in is a little additional box, use a meter ruler. So that allows you to remember, by using a flow map like this, where you add little additional boxes for the equipment, it means that you're less likely to forget to put in the name of the equipment when you're talking about making measurements. Okay, right, you need to also include, you must include the description of how to calculate the wave speed. So once you have your frequency measurement and your wavelength measurement, you must include a description of how to calculate the wave speed. And for this experiment, what we said was that the frequency is the independent variable. So we're going to change the frequency to try to achieve each of the patterns in turn. So that's our independent variable. So we need to include these results in a table to show our measurements for each of the patterns. So the results table, what would we need? Well, we need to have frequency, which is measured in hertz. We need to have the wavelength, which is measured in meters. And eventually we're going to have the wave speed when we do our calculation. So here we have our table of results. You've noticed that I've left a little gap here. What is actually quite useful to do when recording this experiment is to have the diagram of the stationary wave. So you'll have your first frequency value, and that's the one that produces the wave that looks like this. And then for the second one, it produces the wave that looks like this. And for the third one, the wave that looks like this, and so on. As many of these results as you're able to achieve. Now, when we turn the page over, we see that we have some results, some typical results given for this experiment. Here, the results are shown for three waves. So we have the frequency of 5 Hertz, 10 Hertz, and 15 Hertz. So this first one was for the pattern, the fundamental looks like this. The second one was for the pattern looks like this, and the third one is for the pattern that looks like this. What you'll see in reality as you do this experiment, the size of these oscillations becomes smaller as we go from the lower frequency one to the higher frequency ones, and it's often more and more difficult to find the patterns after this third one. So very often there's only 2 or 3 values given. In this case, they have achieved 3 values. Okay, so these are the values. That was the frequency, and we're asked to calculate the wave speed, and we know that the wave speed is given by the wave equation. So that is frequency times wavelength. So we need to use these values in the wave equation. So for the first one, the wave speed is equal to frequency times wavelength, which gives us the wave speed is equal to 5 multiplied by 3.38. So that gives me a value of 16.9 meters per second. And then for the second one, it's exactly the same thing. The wave speed is equal to frequency times wavelength. In this case, I got 10 multiplied by 1.68. So that's going to give me 16.8 meters per second. And then finally, we have V is equal to 15 multiplied by 1.12, which gives me a speed of, again, 16.8 meters per second. Okay, so we have calculate the wave speed, complete the table. So the wave speed, if I was to take the average of these 3, then I get a wave speed of 16.8 meters per second. Comment on your results. What is the effect of changing the frequency on the wavelength? So as frequency is increased, wavelengths, well, what happens, this is the length of the string. As we increase, the wavelength decreases. Notice in this question where it says, what is the effect of change in the frequency? It is not sufficient to say change in the frequency changes the wavelength. You have to say what actually happens. So it's as the frequency is increased, the wavelength decreases. As the frequency is decreased, the wavelength increases. You need to say how the wavelength is changed, not just that it changes. What is the effect of changing the frequency on the wave speed? We can say that increasing or decreasing the frequency has no effect. And that's what we expected. We expected that in a particular material, the wave speed should always be the same. And that's what we find from the experiment. Now, for the last part of writing up an experiment, very often we're asked to think about how well did the experiment work? Did the experiment work well? Did it not work well? Were there any possible sources of errors in our experiment? And they generally come into two types. We've got random errors and systematic errors. And it's important to know the difference. So a systematic error, this is an error where it's always present in the measurements. So an example of that would be if we were measuring the mass of something, but our balance, when we were using our balance to measure the mass, it was already reading, let's say, 0.1 kilograms before we put the objects onto the balance. That would mean that whatever measurement we made, we're always measuring 0.1 kilograms too much. So a systematic error, we always have this exact same mistake in all our readings. So how do we deal with that? We need to remove the error from all measurements. So in the case that I was talking about where we had a measurement of 0.1 kilograms that was too much for all of our measurements, we deal with that by subtracting 0.1 kilograms from all our results. Now a random error is different. This is where this is something like a measurement error, and it can be different for every measurement. So sometimes we might measure something as being slightly too large than what it actually is. Sometimes we might take a measurement that's slightly too small to what the value of the actual measurement is. So this can be because misreading the equipment, or because there's some slight effect in the environment that affects our results. So this is something that can happen either making the measurement too large or too small. So to deal with this, we can't always just subtract something as we do for systematic error. Here what we need to do is we need to deal with the fact that sometimes the measurements are too large and sometimes they're too small. So we deal with this by repeating measurements and taking the average. So whereas for systematic error, it's always the same. So we just need to remove that error from all our measurements. The random error is different in every measurement we make. It can be make it too large or too small. So we deal with that by repeating the measurements and then taking the average. Okay. So in this case, what sources of systematic error might we have? Well, systematic error might be, for example, we might have made a mistake in the measurement of the string. So we made that measurement once and then we use that measurement to work out our wavelengths, because here we're saying that the wavelength is 2 times string length here, the wavelength is equal to the string length here, the wavelength is equal to 2/3 of the string length. So if we made a mistake in the original measurement of the length, that mistake would appear in all our results. So we'd have to deal with that for all our results. However, so a systematic error for this case might be something like this, where we've made a mistake in our original measurement of the string's length. The random error here could be, for example, in the measurement of the frequency. So here, the hard part of this experiment is making sure we've got this pattern exactly right. So we might have, in some cases, our frequency is slightly too low, or in some cases, the frequency that we set is slightly too high. So that might mean that we get a random error in the measurement of our frequency. So how could we deal with that? Why might this occur? It is difficult to get the exact position or exact pattern on the string So as we approach the frequency that creates this pattern, the pattern starts to form whenever we're slightly below this frequency, and then it becomes most clear when we're at the correct frequency, and then it gradually goes away as we move away from that frequency. So we might be slightly too small or slightly too large when we try and measure these frequencies. So how can we deal with this? So we can repeat measurement of frequency for each of these patterns and average. So random systematic errors can occur in any experiment. If it's systematic, we need to remove the error from all our measurements. If it's random, the best way to deal with that is through repeating the measurements and taking the average. So that concludes the 3 lessons for the wave experiments. What you need to do now is to complete these questions, which are exam questions based on the wave topic. So you've got 3 questions to do, and once you've completed the questions, you need to correct your work in green pen. I suggest you do these questions in 2 colored pens. So if you start by using a black pen, and this is where you have closed book. That means you're not using any of your notes or any textbook or revision guide to help you. You just try to answer the question, and you can give yourself roughly 1 minute per mark to do the questions. So we've got, for the first question, we have got 10 marks. Second question, we've got 7 marks, 17, and the third question, we've got 30 marks, so roughly, so around about 30 minutes. So you give yourself around about 30 minutes and try and complete as much as you can. Then you use a blue pen. So this is open book. You can use any resources you like to help you. You can use your revision guide. You can use the notes that you have inside your pack. You can use the internet, whatever you want to try and add to your answers. There's no time limit, so you can spend as much time as you want doing this. So then when you correct using the answers at the back, you end up with 2 scores. 1 for the black pen and 1 for the blue pen. And that's what you will be sending as a message and show my homework to say, what score did you get? Closed book, timed, what score did you get with the blue pen? And you send those to myself and Mr. Milne on Show My Homework.